On the morning of November 24, 2025, something subtle but extraordinary was recorded at NASA's Goldstone Deep Space Communications Complex. The object known as 3I-ATLAS, long categorized as an interstellar comet, had slightly but definitively altered the orientation of its spin axis. Not drastically, not with the kind of violence we associate with tidal disruption or impact. This was something else, something more deliberate in appearance, a slow, steady realignment calculated down to the arc-second. To the untrained eye, such a shift might seem trivial. Comets tumble, rotate, and precess all the time. Their chaotic spin is often shaped by asymmetrical outgassing, especially as they near the Sun. But this wasn't a chaotic tumble, it was smooth, it was geometric. And most strikingly, it resulted in the rotational pole of 3I-ATLAS coming into alignment with Earth's orbital plane. That alignment was confirmed independently by the Deep Space Network, the Chajnantor Millimeter Array in Chile, and orbital telemetry from ESA's Solar Orbiter. All three showed that Atlas's angular momentum vector had shifted by exactly 23 degrees, mirroring Earth's axial tilt to a precision margin of less than 0.5%. This was not expected. To understand the significance of that number, 23 degrees, you have to understand Earth itself. Our axial tilt is responsible for the seasons, for the distribution of climate, and for the evolution of all biological rhythms on our planet. It is a foundational constant of our environmental dynamics. That 3I-ATLAS would adjust its spin vector to match that angle, on this specific date from its current trajectory, defies orbital probability by several orders of magnitude. There's no natural mechanism based on known comet behaviour that could produce such a targeted reorientation this late into a hyperbolic trajectory. It is simply not something comets do. The rotation itself was first noticed not visually, but spectrally. Analysts reviewing spectrographic line broadening in the ultraviolet band saw something strange. The Doppler broadening of emission lines from nickel ions and carbon monoxide had changed subtly overnight. At first, it was assumed to be an instrumental artifact, a recalibration delay in the Doppler tracking algorithm. But the anomaly persisted. Further scans revealed that the line-of-sight velocities of certain jetting regions on the comet's surface had decreased while others increased, consistent with a changing spin angle, not acceleration but redirection. Within 6 hours, the change was confirmed by visual imaging. Using stacked exposures from the Las Cumbres Observatory Global Telescope Network, researchers overlaid the comet's coma structure from previous nights and noticed a consistent pattern shift. Jets once firing away from Earth were now gradually rotating toward the Earth-facing hemisphere. The geometry was unmistakable. 3I-ATLAS was adjusting itself, not away from solar radiation pressure, not in reaction to solar wind torque, but toward Earth. This shift had implications far beyond orbital dynamics. When a rotating object in space realigns toward a gravitational body, it changes not just the angle of radiation reflection, but also the directionality of any mass or energy emissions. And within 90 minutes of the realignment, Earth-based instruments began detecting structured pulses, modulated emissions that, until now, had no previous orientation toward our planet. The realignment wasn't just physical, it was functional. Was this behaviour the result of natural outgassing torque from uneven heating? Or was it something more structured, perhaps driven by internal mass distribution or resonance effects caused by a sudden chemical transition inside the nucleus? That question is still under investigation. But the timing, the alignment, the geometry, they all suggest one thing. Earth is no longer watching 3I-ATLAS. 3I-ATLAS is now watching Earth. Roughly 10 hours after the rotation event of 3I-ATLAS, something changed. Not in its orbit, not in its mass, but in its light. High-altitude observatories in Chile and Hawaii, along with the orbital X-ray telescope NuSTAR, independently registered a sudden sharpening of emissions across multiple bands. What had once been diffuse radiation, thermal and UV glow consistent with sublimating cometary ice, was now narrowing. Not dimming, not fading, but converging, like a flashlight focusing its beam. This shift wasn't symbolic, it was measurable. On standard spectrographs, Atlas's emission profile had always been wide, irregular, scattered across multiple bands as expected from chaotic gas and dust dispersal. But now a new peak emerged. a coherent spike in the soft X-ray range, centered at approximately 0.53 keV, a wavelength rarely associated with comets and far outside the normal solar reflection spectrum. Even more unusual was the geometry of the emission. Instead of radiating outward in a radial pattern from the nucleus, the energy now appeared to be collimated, focused into a narrow directional cone, measuring less than 4 degrees wide. The direction of that cone? Earth. Beam convergence in astronomical terms is rare. Natural objects don't focus their emissions unless a magnetic or structural lens is at play. Pulsars can do it, some quasars, but comets? Never. Comets release volatiles, dust and plasma in messy, irregular flows, governed by surface fractures and thermal differentials, not engineered geometry. The very idea of beam collimation from a hyperbolic interstellar object would normally be dismissed outright. Except this wasn't theory, this was observational data. The beam first registered as a spike in soft X-ray flux on an instrument aboard the ESA solar orbiter, stationed sunward of Earth at the time. That beam then passed through the Chandra X-ray Observatory's field of view, where it was confirmed as not only real, but also pulsed. The timing between pulses? Just under 80/6400 seconds, exactly 1 Earth sidereal day. Too precise for coincidence. Initially, the beam was assumed to be a focused region of outgassing caught by sunlight, perhaps a narrow vent or exposed fracture releasing high-energy particles, but time-resolved spectroscopy debunked that theory. The emissions were modulated, fluctuating in amplitude and frequency in ways that implied structure. This wasn't random venting. It was controlled decay, a signal perhaps, or at the very least a pattern. By the time Earth's rotation brought Arecibo's backup dish into line with the beam, radio silence became a pattern. At multiple wavelengths, standard carrier noise dropped sharply, not due to interference, but absence, a form of selective transparency, as if the region under the beam was somehow being filtered, not blocked, but observed in a specific band, with everything else muted. The convergence was temporary, lasting just over 9 hours, but it repeated 22 hours later, almost to the minute, and each recurrence grew tighter, more focused. Observatories began cataloguing the Earth-facing intervals. National weather satellites logged unusual ionospheric turbulence during beam alignment. Ground-based geomagnetic sensors detected faint harmonics in the ELF, extremely low-frequency range. None of these effects were damaging. None were energetic enough to cause harm. But their structure was unsettling, because randomness doesn't repeat. Noise doesn't align with planetary rotation, and thermal emissions don't pulse in X-ray frequencies. Whatever this beam was, it wasn't casual, it wasn't chaotic, it was selective, it was directional, and most disturbingly of all, it appeared to be intentional, not in a human sense, not as communication, but as focused observation, a cone of energy wide enough to envelop a region of Earth, narrow enough to exclude the rest, not the whole world, just a part of it. At exactly 4:17 a.m. UTC, just hours after 3I-ATLAS's converged beam had stabilized over the Pacific sector, an anomaly was detected, not from above, but from beneath. 2 powerful low-frequency radio arrays, one located in Western Australia and the other in central India, simultaneously reported faint Doppler-shifted returns from a signal that had not originated from Earth-based transmissions. Instead, the source was triangulated to a vector aligned with 3I-ATLAS's active beam window, a convergence that had just swept Earth's upper atmosphere. The readings were subtle, a microsecond delay, a measurable frequency stretch, but unmistakably real. The signal had bounced. To radio engineers and ionospheric physicists, this might seem routine at first. Earth's ionosphere reflects, refracts, and absorbs radio waves depending on their frequency. It's why shortwave radio works across continents. But these signals weren't from Earth. They were coming into the atmosphere, grazing the F layer and echoing back with distortions that made no conventional sense. The frequency? 3.48 megahertz, a strange band nestled just between military aviation and ionospheric heating research. The shape? Narrow band. The modulation? None. But the signal strength grew stronger at night over oceans and fell silent over continental land masses. That alone raised eyebrows. When teams at Stanford's VLF laboratory cross-referenced the data, they discovered that this wasn't the first time such an echo had been captured. In fact, nearly 14 microbursts had been detected in the last 48 hours. They'd simply been dismissed as tropospheric scatter or long-path lightning artifacts. But now, in the context of 3I-ATLAS's focused emissions, the pattern became clearer. The echoes were only occurring when the beam path intersected with Earth's night-side ionosphere. In other words, the comet was scanning from the dark. Why would that matter? At night, Earth's ionosphere behaves differently. The absence of solar UV causes the D layer to collapse, while the F layer stabilizes and becomes more reflective, especially to VLF and ELF radio. These are the same conditions that submarines and military operators use for long-range communications. But here, they were being leveraged, not by Earth, but seemingly by an object millions of kilometers away. And here's what's more unsettling. The Doppler shift in the returning echoes exactly matched Earth's rotational velocity, not orbital, not axial tilt, but surface speed at equatorial regions down to the last decimal. The signals were being corrected in real time for Earth's spin. In other words, 3I-ATLAS wasn't just emitting. It was measuring the distortion, using the echo of its own energy bouncing off our atmosphere as a passive probe. This kind of technique is used in Earth science missions like SR, synthetic aperture radar, and ionospheric tomography. But never has it been observed as a side effect of a natural interstellar object. That raises a question. If ATLAS's beam is emitting across multiple bands, and it is, could the Doppler echoes be a calibration mechanism? A way for the object to refine its beam profile by observing how its pulses return from Earth? Or is it using the atmosphere itself as a kind of refractive lens, bending and shaping its emissions to scan below the cloud line to analyse the surface? A disturbing thought surfaced at MIT's Haystack Observatory. If the signals are being used for surface mapping that would imply resolution, detail, intent, not communication, surveillance, the data is now under embargo while joint teams from NASA, ESA and JAXA analyse the waveform structures in more depth. But one thing is clear. This wasn't noise, it wasn't terrestrial, and it wasn't random. It was a pulse that entered Earth's airspace, bounced off our highest atmospheric layer, and returned with information. And ATLAS listened. At 6:12 UTC, on the same morning that Earth entered the observation cone of 3I-ATLAS, a brief but powerful infrared burst was detected above the Central Pacific. It lasted only 3.2 seconds, but its signature was so distinct, so anomalous, that 4 separate monitoring platforms flagged it as a potential false positive until the redundancy confirmed otherwise. The flash originated at high altitude, approximately 110 kilometers above the Earth's surface, just within the lower thermosphere. It wasn't a meteor, it wasn't a satellite burn, and it wasn't lightning. All natural phenomena were ruled out within the first hour. What remained was far more difficult to explain. The object known as 3I-ATLAS had released a narrowband infrared pulse that intersected with Earth's upper atmosphere in a location devoid of ground infrastructure, outside any known surveillance zone. It struck just north of the equator, west of the Line Islands, well within the beam trajectory previously documented by NASA's Deep Space Network and confirmed by ESA's solar orbiter. The wavelength of the burst fell into the 4 to 5 micrometer band, a range often used in military-grade thermal imaging and atmospheric heat mapping. But this wasn't imaging equipment. This was a comet, an interstellar object accelerating out of the solar system, and yet the pattern of the flash, the Gaussian symmetry, the rapid rise-fall profile, and the peak intensity mirrored controlled thermal pulses generated by Earth-based infrared lasers. The source of the flash was triangulated using data from the Goose West satellite, the VIIRS sensor aboard Suomi NPP, and Japan's Himawari 9. All 3 satellites detected the spike within 0.3 seconds of one another. Their readings overlapped to confirm that the pulse was not only directed, but localized to a 90-kilometer wide corridor in the atmosphere. It didn't penetrate, it didn't explode, it simply passed through. But as it did, ground-based sensors in Hawaii and French Polynesia recorded transient heating in the stratosphere. A 0.2 degrees Celsius jump. Not dramatic, but statistically impossible without a causative energy input. The energy required to create such a temperature bump over such a volume exceeds 300 gigajoules, equivalent to a small nuclear device, yet there was no shockwave, no radiation spike, only heat, and then nothing. The pulse ended as abruptly as it had begun. Satellites resumed nominal readings, the atmosphere returned to baseline, but one thing didn't reset: the airglow. For 90 minutes following the flash, sensors from the timed satellite recorded an unusual infrared airglow pattern at the same altitude as the pulse's path. The emissions matched no known photochemical process in Earth's upper atmosphere, but they did match plasma emission spectra from nickel ions, previously observed in the wake of 3I-ATLAS at both Mars and Venus. So what happened? The leading hypothesis among infrared physicists is that 3I-ATLAS, for reasons not fully understood, swept an active thermal pulse across Earth's upper atmosphere, possibly as part of a wider observation sequence. The beam could have been used to excite trace particles, cause secondary emissions, or map atmospheric composition through stimulated fluorescence. But the shape of the burst complicates that theory. It wasn't diffuse, it wasn't broad, it was tight, modulated and symmetrical, a hallmark of signal testing, not passive scanning. In essence, 3I-ATLAS pinged Earth, not with radio, not with optics, with heat. A momentary flash from a comet millions of kilometers away, aimed directly at our rotating planet, at the precise moment Earth's orientation placed it in range. It left no crater, no ash, no trace of visible change. But it did leave a question. What kind of object uses heat as its probe? And why was it focused on us? At 0710 UTC on the morning of November 24, 2025, a quiet directive was issued from the Space Telescope Science Institute in Baltimore. It wasn't announced, it wasn't public, but it was real and confirmed by 4 separate logs transmitted from the James Webb Space Telescope itself. The telescope had suspended all other scheduled observations. No more exoplanet atmospheres, no more early galaxy studies, no more deep field mosaics. Instead, JWST rotated to face one thing: 3I-ATLAS. This marked only the 3rd time since its deployment that JWST's observation queue had been overridden. The previous 2 were for interstellar object 2I Borisov and the emergency imaging of DART's asteroid impact. But this override came with no external impact, no mission event, no planetary emergency, only a single line in the system change log: priority reroute, anomalous thermal signature and beam coherence. The decision came after the infrared flash event had passed through Earth's upper atmosphere. Infrared specialists at NASA's Goddard Space Flight Center had flagged the 3I-ATLAS data as inconsistent with known comet activity. When analysts matched the pulse's emission line to archived readings from the comet's prior Venus encounter, they saw a startling overlap. A similar mid-infrared spike, focused and coherent, had registered in the sulfuric layers of Venus's upper atmosphere. It wasn't an isolated phenomenon, it was a pattern. JWST's unique capabilities made it the only telescope in existence capable of capturing high-resolution mid-infrared spectroscopy from 3I-ATLAS's beam region, especially in wavelengths between 4.5 and 14 microns, where complex molecular transitions occur. And what it saw next startled the team. The MIRI, mid-infrared instrument, onboard JWST began detecting structured emission bands, not noise, not outgassing, but molecular signature stacking. This phenomenon occurs when a source emits in such a way that multiple chemical compounds fluoresce together in synchronized resonance. The stacked compounds: nickel carbonyl, hydrogen cyanide, ammonia derivatives, and faint traces of phosphine. The combination of those molecules doesn't happen naturally in interstellar space, certainly not in the absence of solar input. But ATLAS wasn't simply reflecting light, it was emitting something that stimulated molecular activity. As JWST continued its lock, its instruments began experiencing oscillating signal distortion. Interference not caused by the sun, cosmic rays, or Earth's own magnetic field. The interference came from coherent wave modulation in the infrared beam itself. In other words, 3I-ATLAS's emissions had internal structure: timing, repetition, spacing. What does that imply? On Earth, we use coherent beams with structured modulation for data transmission: lasers, fiber optics, LiDAR. In nature, that sort of coherence is rare, and when it does happen, such as in mesas, It comes from very specific, high-energy astrophysical processes. JWST, orbiting at the Sun-Earth Lagrange point 2, was perfectly positioned to avoid Earth's own heat signature. This gave it a clean line of sight to 3I-ATLAS and its emissions, and what it recorded couldn't be explained by comet physics. The emission coherence tightened, the beam narrowed, and then, inexplicably, JWST lost lock, not because of hardware failure, not due to repositioning or a safe mode trigger, but because the target vanished from its thermal profile. 3I-ATLAS, for a full 78 seconds, emitted no detectable thermal radiation, a cold silence in the infrared, and then it reappeared, not diffused, not diminished, but stronger, with a shifted pulse frequency now centered closer to Earth's black-body signature. It had recalibrated, not away from JWST, but seemingly to match it. This forced JWST to pause tracking and upload new calibration models, and for nearly 6 hours no other targets were observed. No galaxies, no stars, just a single object, millions of kilometers away, watching, shifting, and, apparently, responding, as Earth continued rotating beneath the emission cone of 3I-ATLAS. Another region of space, one far less visible to the public eye, began registering strange shifts. In the vast stream of solar particles flowing outward from the Sun at over 400 kilometers per second, something unexpected began to form, a magnetic knot. It was first detected by the Parker Solar Probe, then confirmed by instruments aboard the Solar and Heliospheric Observatory, SOHO. The solar wind in the vicinity of 3I-ATLAS was behaving in a way that deviated sharply from all predictive models. Instead of flowing past the comet's tail and continuing outward, as it does with every known comet, the stream bent inward, creating an unnatural eddy, a spiral-shaped inversion that briefly redirected charged particles back toward the Sun. This defied conventional heliophysics. Solar wind is a continuous plasma flow dominated by high-velocity protons and electrons. When it meets the tail of a comet, the interaction typically creates two distinct structures: a dust tail, composed of larger grains pushed by radiation pressure, and a plasma tail, made of ionized gases carried by the magnetic field lines of the solar wind. The result is predictable. The tail always points away from the Sun. But that wasn't the case here. Instead, 3I-ATLAS's plasma tail curved sharply back toward Earth's orbital plane, even as the comet moved away from the Sun. And the more scientists studied the shape, the clearer it became. The tail wasn't reacting to the solar wind, it was shaping it. Why does this matter? Because for an object with no magnetic field of its own, no solar engine, and no ion thrusters, altering the direction of charged solar particles on such a scale should be impossible. Yet particle flux measurements from the ACE spacecraft, stationed at the L1 Lagrange point between Earth and the Sun, showed a noticeable dip in solar wind density, beginning precisely when 3I-ATLAS entered beam convergence mode. That density drop wasn't global, it was directional, confined to a corridor roughly 30 degrees wide, originating near Atlas's trajectory. Within that corridor, the solar wind slowed, coiled, and in some cases reversed direction. This behaviour has no known precedent in cometary physics. One possibility is that 3I-ATLAS's emissions were somehow ionizing the surrounding interplanetary medium, creating a local region of enhanced plasma density that deflected incoming solar particles. But that doesn't explain the shape. The inversion pattern wasn't radial or spherical. It followed the same helical twist previously seen in magnetic flux ropes, structures typically associated with solar coronal mass ejections. In other words, 3I-ATLAS's tail was behaving like a solar event, not a passive object. The implications are enormous. If an interstellar object can interact with solar plasma fields this way, it means it is operating on electromagnetic principles that we've only begun to understand. Principles that may involve induced magnetospheres, active field shaping, or unknown charge interactions with the heliospheric current sheet. A quiet alert was issued internally to heliophysics labs across the US and Europe, not for public release, not yet, but enough to redirect observation time across multiple platforms. New models were written to simulate what a reactive plasma field might look like, one that doesn't just receive energy from the Sun but pushes back. And here's what unnerved some researchers the most. The same pattern, the same twisting reversal in particle velocity, was observed at Mars on October 3rd, then again at Venus on November 3rd. Both times 3I-ATLAS passed by. Both times the solar wind bent. Now, on November 24th, it happened again, over Earth. 3 planetary interactions, 3 magnetic anomalies, 1 object, and a tail that doesn't follow light. It follows something else. At exactly 09:46 UTC on November 24th, 2025, the La Palma Observatory in the Canary Islands recorded a familiar but deeply troubling spectral signal. A strong emission line at 362.0 nanometers, corresponding to ionized nickel, Ni+, had reappeared in the spectrographic data from 3I-ATLAS. It was the same spectral line that had confounded scientists during the object's earlier interactions with Mars and Venus. But this time, it was brighter, sharper, more concentrated. And unlike previous detections where the nickel emissions were isotropic and diffused across the comet's coma, this time the signal was directional. It was traced to a specific sector of the object's emission cone, and more disturbingly, Earth was directly in its path. This was not ordinary nickel, it was refined. Spectroscopy confirmed the absence of iron lines near 373.5 nMev, which would normally accompany any natural nickel release due to their joint formation in stellar nucleosynthesis. In natural cosmic environments, nickel and iron are nearly inseparable. Whether in asteroids, comets, or meteorites, they appear in ratios that reflect the cosmic abundance forged in supernovae, typically around 1:18 nickel to iron. But here, again, the iron was missing. The spectral purity of the nickel emission matched previous observations at Mars and Venus, where it had appeared to originate from a chemical separation process, potentially similar to Earth's MOND process, a method of vaporizing and purifying nickel using carbon monoxide. The spectral line's shape, width, and brightness suggested not random outgassing, but focused expulsion, as if the comet was venting chemically processed material in our direction. Why now? Why Earth? Just before the emission peak, the James Webb Space Telescope had gone into observational lock on 3I-ATLAS and recorded stacking molecular emissions that included nickel-carbonyl compounds, volatile intermediates not commonly found in space. This reinforced the hypothesis that ATLAS wasn't just outgassing, it was operating under conditions that simulate industrial chemical refinement. But here's where the data gets more troubling. Within 90 minutes of the nickel emission detection, high-altitude balloons launched from the Mauna Loa Observatory in Hawaii detected elevated nickel-ion concentrations in the upper stratosphere. Not enough to be hazardous, but enough to be unexplainable. Earth's atmosphere does not contain free nickel in ionic form. When such ions are detected, they typically originate from industrial sources like metallurgical facilities or volcanic plumes. But there were no eruptions, no fires, no factories nearby. The timing was precise. The directional vector pointed back to ATLAS. The signal had arrived. And then another detail emerged. A team at the University of Tokyo, running real-time comparison models between Mars, Venus and Earth observations, noticed something consistent. Each time the nickel signal peaked, it was shortly followed by changes in ionospheric pressure, airglow emissions and plasma refraction. Nickel wasn't just being released, it was doing something to local space environments. On Earth, nickel is catalytically active in many of the oldest metabolic reactions in biology. It assists in hydrogen oxidation, methane production, and carbon fixation. In laboratory experiments simulating early Earth, nickel surfaces are used to promote the formation of amino acids and nucleobases. Now, that same element, purified, isolated, and delivered in measurable concentrations, was falling into Earth's upper atmosphere. Not in tons, but in grams. Enough to trigger a new kind of question. Is this random chemistry? Or is 3I-ATLAS seeding environments deliberately because Mars was altered, Venus was stirred, and now Earth is being exposed? 3 planets, 1 rare element, always delivered pure and never with iron. At 11:03 UTC on November 24th, 2025, a high-altitude balloon launched from the Kiruna Geophysical Observatory in northern Sweden transmitted data that immediately halted every ongoing routine analysis. The sensor had detected hydrogen cyanide, HCN, in Earth's mesosphere, and not in trace amounts. The measurement showed localized concentrations over 0.4 parts per billion, clustered between 85 and 95 kilometers in altitude. Hydrogen cyanide is not a normal part of Earth's upper atmospheric chemistry. It's occasionally produced in wildfires, volcanic plumes, and during high-altitude aircraft combustion. But its presence is rare, unstable, and transient. HCN is a highly reactive molecule, quickly broken down by sunlight, water vapour, or oxygen radicals. But this sample was none of those. It wasn't from below, it was from above. Using real-time wind and dispersion modelling from NOAA's High Altitude Research Division, the plume was traced to a specific point of entry, aligned almost perfectly with the beam vector from 3I-ATLAS that had passed over the Pacific roughly 6 hours prior. The atmospheric models showed a top-down dispersion pattern consistent with external deposition, not ground-based outgassing. And then came the corroboration. The atmospheric chemistry experiment, ACE's satellite, orbiting at 650 kilometres, had also recorded an HCN spike, this one in the infrared band, detected via occultation during sunrise limb scans. This confirmed the molecule's spectral signature, and more importantly, its altitude layer, well above commercial aviation and even above the stratospheric ozone layer. The fact that HCN was now present in the mesosphere, coinciding with both the nickel ion detection and the infrared flash, led atmospheric scientists to consider an unnerving possibility. Earth was not generating this compound. It was being seeded with it. To understand the weight of that discovery, you have to understand what HCN means in astrobiology. Hydrogen cyanide is one of the most versatile prebiotic molecules in the known universe. In controlled conditions, it forms the base pairs that constitute RNA. It can polymerize into adenine, one of the 4 fundamental components of DNA. It reacts with formaldehyde to create amino acids, and under cold conditions it condenses into stable crystalline forms that preserve molecular information for decades. In short, HCN is the Swiss Army knife of life chemistry, and now it was in Earth's upper atmosphere, above the ozone, in a region where UV exposure would normally destroy it in seconds. But satellite imaging showed something different, a brief, localized UV shadow, just moments before the HCN spike, a window of shielding, a transient shield. It matched the infrared airglow pattern seen earlier, the one caused by ionized nickel, and suggested that the beam from 3I-ATLAS had not only delivered material, but had created momentary shelter for its survival. This was not passive interaction, it was timed delivery. Within 45 minutes, stratospheric wind models showed the HCN diffusing south, curling around the equator and descending gradually, right into the altitude band where cloud condensation nuclei form. If the molecule reached the lower stratosphere, it could seed storm systems, get trapped in ice crystals, or even enter Earth's global water cycle. It would be diluted, of course, safe, invisible to the naked eye. But it would be there, and that, more than anything, made researchers stop, because we weren't looking at a singular anomaly anymore. We were seeing the same pattern repeated, at Mars, then at Venus, now at Earth. The same compound, the same molecular structure, the same timing, always delivered after the beam alignment, always detected in the upper atmosphere, always paired with nickel. These are the molecules that don't just survive, they build, and now they're here. The question isn't where they came from. The question is, what happens when they land? At 12:19 UTC on November 24, 2025, a magnetometer stationed across the northern hemisphere detected a deviation. It was brief, it was subtle, and it was consistent across every node. Earth's magnetic field, our primary shield against cosmic radiation and solar wind, tilted by just under 0.015 degrees in what researchers called a non-cyclical drift anomaly. It wasn't large enough to disrupt GPS. It didn't trigger alarms at ground level, but in the realm of planetary geophysics, even a fraction of a degree, if unexplained, carries enormous weight. The anomaly lasted 72 seconds, and then it reversed. What makes this event so strange is not simply the shift, but the fact that it occurred in complete absence of geomagnetic storm conditions. There were no solar flares, no coronal mass ejections. The solar wind speed was well within its average range, hovering at 410 km per second, and the interplanetary magnetic field was stable. In other words, the field should have held steady. But it didn't. The shift was first flagged by the SuperMag Global Magnetometer Array, a coordinated network of observatories from over 30 countries. When data from Svalbard, Tromsø, and Magadan were overlaid, the drift pattern showed a coherent wave, not centred at the poles, but beginning near the geomagnetic equator, an area less prone to sudden magnetic movement. Even more compelling was the alignment. The wavefront of the drift corresponded to the exact ground track of 3I-ATLAS's converged beam vector, just 300 kilometres above Earth's surface, sweeping longitudinally from west to east. It was as if the beam had nudged the planet's invisible shield, not forcefully, but with precision. To test that theory, teams at the European Space Agency's SWARM mission, which monitors Earth's magnetic field from orbit, ran a high-resolution vector analysis. They discovered a phase inversion in one of the scalar field components, a ripple-like distortion that propagated eastward in sync with the planet's rotation. And that ripple wasn't natural, its waveform was uniform. Its propagation speed matched Earth's rotation to within 0.02%, and its return to baseline was symmetrical, qualities that strongly suggest a resonant excitation, not an impulsive hit. But from what? One hypothesis proposes that 3I-ATLAS, through its emission cone, delivered not just energy or particles, but electromagnetic coherence, a type of structured radiation capable of resonating with Earth's magnetic shell. The energy required for such a resonance wouldn't need to be massive. It would only need to be precisely tuned. This is how certain radio frequencies cause constructive interference in metal bridges, or how microwave beams can trigger resonant heating in water molecules. But Earth's field isn't a metal object. It's a dynamic magneto-hydrodynamic shell generated by the movement of molten iron in the outer core. To interact with it, let alone influence it, requires an understanding of magnetic topology far beyond natural comet behaviour. And yet, it happened. The drift also coincided with another rare event, a sudden drop in Schumann resonance amplitude. These are the natural electromagnetic frequencies of the Earth ionosphere cavity, essentially Earth's own heartbeat. The amplitude decrease was minor but synchronized exactly with the magnetic deviation. Multiple observatories now believe the two events are linked. If so, that implies 3I-ATLAS didn't just cause a geomagnetic twitch. It briefly altered the electromagnetic mood of the planet itself. Why? How? Those questions remain unanswered, but one thing is certain. This was not background noise. This was not solar weather. This was not terrestrial. It was an interstellar object, and it reached out, however briefly, to touch the planet's pulse. At 1342 UTC, shortly after the nickel signal faded and Earth's magnetic field began stabilizing, a quiet anomaly was flagged at both Lagrange point 1, L1, and Lagrange point 2, L2. These are two of the most strategically important locations in space, gravitational balance points where satellites can maintain stable positions with minimal fuel use. At L1, positioned between Earth and the Sun, sits the Deep Space Climate Observatory, DSCO-VR, and ESA's solar orbiter. At L2, behind Earth in its orbit, are the James Webb Space Telescope, Gaia, and various classified European and American assets. Both points lit up with alerts. The sensors weren't just measuring routine solar activity or radiation spikes. Instead, they were registering a kind of waveform displacement, not in space itself, but in the sensor baselines. Onboard accelerometers at L1 recorded a fractional but undeniable change in frame tension, a kind of minute vibration not linked to onboard activity, solar wind, or micrometeorite impacts. At the same time, instruments at L2 flagged inertial offsets in long-range telemetry systems. The signals weren't garbled, they weren't broken, they were shifted by only 1.6 arc-seconds. That may sound small, but for satellites that rely on sub-arc-second precision for both pointing and navigation, it's the equivalent of a hand brushing a needle while it's threading a spacecraft through a pinhole. What caused it? The direction of the shift gave the first clue. When data was overlaid from multiple platforms at both Lagrange points, a single vector emerged. The disturbance was radial from 3I-ATLAS. More specifically, it was orthogonal to the beam vector that had passed through Earth's upper atmosphere only hours earlier. It was as if 3I-ATLAS had pulsed outward, deliberately or incidentally, and the ripple hit both L1 and L2 simultaneously. Impossible? Under normal circumstances, yes. These points are 2.5 million kilometers apart, located on opposite sides of Earth. No natural event has ever been known to trigger identical sensor responses on both sides of the planet at the same time. But this one did. One explanation being quietly explored within both ESA and NASA suggests that what was detected was not electromagnetic, not gravitational, but something more subtle, a structured inertia field. The phrase sounds like science fiction, but here's what it means in physics terms. When mass or energy causes temporary alteration in the local distribution of inertial reference frames, objects can appear to shift slightly, not because they've moved, but because their background has. This phenomenon has no place in classical mechanics, but in quantum field theory, similar behaviour has been described in relation to vacuum field fluctuations, zero-point energy, and, most provocatively, frame dragging. Normally, frame dragging is a relativistic effect associated with rotating massive bodies like black holes. But here, we're not talking about spin, we're talking about pulse emission from a non-rotating interstellar object, interacting with distant sensor nodes at gravitational equilibrium points. There's no math to support it. Not yet. But the timing, direction, and structure of the shift match no known natural event. And then came the final clue. Both Gaia and JWST briefly entered star tracking recalibration mode, triggered automatically when stellar alignment tolerance exceeds safe thresholds. This happens maybe once or twice per year, typically during solar activity spikes. On November 24, it happened to both, within 3 minutes of each other. Coincidence? Or evidence that Earth's entire observational envelope, from sun-facing L1 to deep space-facing L2, was caught in something like a soft ripple, originating from ATLAS and brushing across the most sensitive points in the Earth-Sun system. Not an explosion, not radiation, just a shift, gentle, measured, but real. At 1411 UTC, one of the European Space Agency's most precise optical instruments, the Optical Ground Station, OGS, on Tenerife, registered an event so rare it has only been seen twice in over 20 years of continuous operation. The stars paused. More precisely, for a duration of 3.2 seconds, the telescope's automated background correction algorithm, which constantly tracks the apparent drift of stars due to atmospheric distortion, Earth's rotation, and orbital precession, logged 0 deviation across all measured vectors. It was as if the sky had become a fixed painting. No shimmer, no drift, no movement, just stillness. The system flagged it as a sensor freeze, a rare but known glitch caused by thermal expansion, or a feedback loop in the optical servos. But internal diagnostics showed no fault. Every subroutine was functioning. Temperature, lens pressure, gyroscope feedback, normal. The system was not stuck. It was simply seeing no movement. This shouldn't be possible. No matter how calm the sky, even under perfect conditions, starlight bends through the atmosphere. The twinkling of stars, the phenomenon known as astronomical scintillation, is ever present due to Earth's turbulent atmospheric layers. Telescopes never record perfect stillness. Even in orbit, gravitational perturbations from the Moon, solar radiation pressure, and Earth's wobble keep instruments in constant minute adjustment. But this time, for over 3 seconds, nothing moved. What makes this more disturbing is what happened next. The telescope's starfield comparison system, which overlays real-time images against stellar catalogues, triggered an error. Background mismatch. Pattern displacement exceeds allowable variance. What does that mean? It means the stars didn't just pause, they shifted. By a fraction of a degree, 0.0072 arc minutes, the entire starfield in the captured image no longer aligned with known coordinates. Not due to parallax, not due to lens error, but as if the background itself had been repositioned. Then, within 2 frames, it returned to normal. This event was logged, tagged as background sync error, and automatically shared with ESA's partner observatories for cross-reference. Within 6 minutes, a similar alert was received from the Cala Alto Observatory in mainland Spain. Their mid-infrared array, while scanning near the same sky sector, logged a pixel compression anomaly that lasted exactly the same duration, 3.2 seconds, 2 independent observatories, 2 separate instruments, same moment, same sky, same result. This wasn't local, it was external. ESA's internal task force began comparing the timestamp with other unusual events from that day. The drift in Earth's magnetic field, the structured emissions from 3I-ATLAS, the nickel signal, the beam convergence, and when overlaid, the moment of the pause landed precisely between the detection of hydrogen cyanide in Earth's upper atmosphere and the triggering of Lagrange point sensors. It was a bridge event, a ripple. If the sky paused, even briefly, it implies a fundamental interference in reference stability. Telescopes use stars as fixed anchors because stars don't shift on human timescales. They are the universe's most reliable constants. If something can cause a coordinated delay, or misalignment, in how we perceive their positions, then that something is operating on a level of spatial influence beyond gravitational lensing or magnetic interference. One possibility quietly raised by senior ESA physicists is the idea of a localized frame distortion. Not time travel, not wormholes, but a short-lived displacement of our observational layer, like a lens shifting slightly in a cosmic camera. Not enough to move Earth, just enough to move what we see. And when everything snapped back, no damage, no residual error, just the logs and the stillness. The kind of stillness you only get when something enormous moves, without a sound. At 15:02 UTC on November 24th, 2025, a weather balloon released from the South Pole Atmospheric Research Station detected an unusual shift in spectral emissions, specifically in the red and green bands between 630 and 557 nanometers. These bands correspond to polar air glow, a natural phenomenon caused by the recombination of atoms in the upper atmosphere, typically after being excited by sunlight or energetic particles from the solar wind. But what made this instance different, alarming even, was the fact that the phenomenon occurred during full polar darkness. There was no solar input, no recent geomagnetic storms, no auroral forecast, and yet the airglow returned. At first, scientists believed the balloon's sensors were miscalibrated, but just minutes later, the Barrow Arctic Observatory in northern Alaska reported the same readings. A sudden uptick in airglow emissions near the magnetic pole, visible even to all sky cameras, creating a faint luminous haze across the upper sky. A soft shimmer, red on the horizon, green streaking overhead. Local Inuit observers described it as a ghost aurora, but it wasn't an aurora at all. It was something worse, or stranger. Airglow normally occurs due to photochemical reactions in the thermosphere. Oxygen atoms recombine after being split apart by ultraviolet sunlight during the day, and they slowly release that stored energy at night, creating faint glows visible under very dark skies. But these reactions require sunlight first, and here there had been none for weeks. The South Pole was locked in its long winter night. No sun, no UV, no particle storm, just silence. Until now. Spectral data from the event was analysed and found to contain non-standard excitation ratios, meaning the energy levels causing the airglow were not matching any known chemical precursors. One proposed theory suggests the energy came from above, specifically from the focused beam that had passed over the poles earlier that morning. When 3I-ATLAS initiated beam convergence over Earth, it didn't just sweep the equator. It passed over both poles, delivering not heat, but what might be called structural energy, a coherence, a trigger, a mechanism capable of re-exciting the upper atmosphere even in the absence of sunlight. And this is where things became more complicated. The airglow lasted longer than it should have. 87 minutes across a wide swath of the southern hemisphere and 53 minutes in the northern polar zone. During this window, multiple observatories reported elevated ionospheric refraction, unusual radar returns and spikes in VLF, very low frequency radio transmissions, some of which were reflecting off layers of the ionosphere that should have been dormant. Essentially, Earth's polar cap became electrically active, as if a day had passed in seconds, but only in the sky. The implications are profound. If an interstellar object like 3I-ATLAS can selectively reactivate the photochemical shell of a planet, without sunlight, without particle injection, then we're dealing with an object that understands planetary excitation protocols, not just chemistry. Control. Airglow is not a flashy phenomenon. It's quiet, consistent, usually ignored. But in the hands of a structured, intentional emitter, it becomes a kind of signal canvas, a way to broadcast without sound, to light up the envelope of a planet without touching its ground. And here's the strangest part. When the glows faded, they didn't decay normally. They snapped off like a switch was flipped. Instant loss, not gradual recombination. This wasn't Earth resetting, it was something else withdrawing, and for a few brief minutes both ends of the planet were awake, glowing in unison, as if answering a call we didn't hear, or acknowledging something we still don't understand. At 1547 UTC, instruments aboard the European Space Agency's Cometary Tracking Array detected a statistically significant increase in the mass of 3I-ATLAS's coma, the diffuse cloud of gas and particles surrounding its core. Initial readings from the Rosetta A2 LIDAR array showed a subtle but measurable densification in the region surrounding the nucleus. Over the course of 48 minutes, particle reflectivity in the visible and near-infrared bands rose by 14%, while radar returns suggested that the overall particulate mass in the coma had increased by nearly 60 metric tons. This wasn't simply more dust being thrown off from the comet. The directionality was wrong. Instead of expanding outward randomly, the additional mass formed a boundary layer, almost like a curtain being pulled around the object. The velocity of the particles also slowed, not accelerated as one would expect in an active comet undergoing sublimation. In essence, the coma was condensing, not erupting, and that alone upended decades of cometary science. Natural comets become active as they approach the sun. Ice sublimates, gas erupts, dust jets form. The coma expands rapidly and chaotically, blown into tails by solar wind and radiation pressure. But 3I-ATLAS wasn't following this script. Instead, it was behaving like a system, a closed-loop environment managing its own exosphere. The sudden increase in coma mass corresponded exactly with the moment Earth's polar airglow lit up, and within that same window, Earth-based telescopes observed a sharpening in the object's outer boundary, as if the new particles were being placed with intention. Analysis from the infrared telescope facility in Hawaii revealed that the particles were not just silicate dust or frozen volatiles. They showed high albedo in the shortwave IR, consistent with materials that have undergone surface structuring, tiny features at the microscopic level that don't arise through explosive ejection or sublimation, but through fabrication or chemical processing. In short, the coma wasn't shedding mass, it was gathering it. This realization raised immediate questions at the ESA's internal planetary response board. What would cause a comet to accumulate mass around itself? Why now? And why during its closest pass to Earth? One possibility: shielding. By forming a denser coma, 3I-ATLAS may have been creating a kind of radiative veil, designed to obscure or filter emissions, perhaps to prevent deeper spectroscopic scans from detecting its true structure. Another possibility: broadcast medium. Some researchers proposed that the coma was being seeded with materials that increase signal coherence, particles engineered or structured to carry information, like how fog enhances laser visibility, or how charged particles can serve as relay amplifiers in plasma communication. And then came the kicker. Simultaneously with the mass increase, Earth-based receivers picked up micropulses from the direction of 3I-ATLAS, short bursts of structured electromagnetic radiation in the UHF band, not strong enough to classify as transmissions, not random enough to ignore. The pulses stopped when the coma stopped thickening. It was as if the cloud was part of a mechanism, a signal field, a body with a voice. Within hours, the coma stabilized again. The total mass increase was confirmed by long-range gravimetric inference to be real, not an observational artifact, and just as silently as it thickened, it held, like something preparing, or protecting, or simply responding. Mass doesn't just appear, not in vacuum, not without force, so whatever 3I-ATLAS is, it's not just moving through space, it's building something around itself, and now that structure, thin, quiet, layered, is looking directly at Earth. At 1628 UTC, a team at the Lunar Reconnaissance Orbiter, LRO Mission Control Center, flagged a low-priority anomaly from one of their routine seismic pingback scans. These acoustic scans, regularly conducted by bouncing signals into the Moon's surface and measuring the returned waveform, are used to map subsurface structure and detect micrometeorite impacts. But this one was different. The signal returned from the Mare Tranquillitatis region, near the Apollo 11 landing site, showed a delay. Only a fraction of a second, but enough to exceed the predicted margin of error by 0.03 seconds, translating to a discrepancy in surface response equivalent to several meters of unexpected impedance. At first, this was considered a timing artifact. The Moon has no atmosphere and very low tectonic activity. Seismic propagation is relatively predictable. But this was not just a delay. It was a shape change. The returning wave had altered amplitude, decayed faster, and exhibited interference patterns not typically seen in natural regolith reflection. Essentially, the Moon echoed the signal back, but differently, like someone briefly modified the material it was bouncing off of. That same hour, ground-based radio observatories, specifically the low-frequency array, LOFAR in the Netherlands, recorded a series of lunar microwave reflections. These pulses reflecting off the Moon's surface appeared to have originated not from Earth, but from the direction of 3I-ATLAS, more than 12 million kilometres away at the time. The waves bounced off the Moon's near side and returned at a slightly altered frequency. The shift was minimal, but consistent. A classic Doppler deformation, but not from velocity, from surface structure. Radar analysts noticed that the Moon's reflection profile, the way it scatters radar, had changed. Not over weeks, not from meteor impacts or slow regolith drift, but within hours, and precisely when the Atlas signal field was aligned with the Earth-Moon system. What does this mean? One possibility is that the Moon served as a passive relay, a natural dish, receiving and reflecting signals from Atlas that Earth's atmosphere would have scattered or absorbed. The lack of an atmosphere, magnetic field, and surface moisture makes the Moon the perfect natural transponder. But the pattern of the echoes suggested more than passive reflection. They carried modulation, subtle amplitude variations, nested in the returning waveform like data hidden in the folds of a radio wave. That's when researchers checked the archived Apollo seismic data and found something chilling. Back in 1969, during Apollo 11's early lunar module landings, a similar delay and signal distortion had been recorded. At the time, it was attributed to uncalibrated hardware. Now, in light of this new event, a reconsideration is underway. Was the Moon always just rock? Or has it been touched before by the same system we're now watching approach from interstellar space? The working theory is bold. 3I-ATLAS, through its converged beam, may be interacting with inertial or electromagnetic surfaces to map or modify how objects reflect structured energy. The Moon, long thought to be silent and inert, briefly responded with a patterned echo, not a random bounce. That echo was recorded. It's now being dissected by ESA's Deep Signal Group. And here's the final twist. The waveform, once enhanced, mirrors a scaled-down version of the same pulse recorded from 3I-ATLAS itself 2 days earlier, when it passed by Mars and left a similar bounce signature on Phobos. Different planet, different satellite, same echo. It's not the kind of signal you send by accident. It's the kind you send to see who's listening. And now, for the first time in over 50 years, the Moon replied. At 17:02 UTC on November 24, 2025, the Infrared Spectral Observatory, ISO, in Chile, began routine scans of the trailing edge of 3I-ATLAS's coma. It was part of an ongoing international effort to map the object's spectral behaviour across the electromagnetic range, from ultraviolet to mid-infrared. What they recorded was not routine. Over a 19-minute window, the spectrograph captured a gradual shift in emission lines, not in intensity, as might be expected from solar heating or outgassing, but in their geometry. Emission lines, in spectroscopy, are narrow fingerprints that indicate the presence of specific elements or molecules. They are perfectly linear under normal observation. Even when broadened by heat or motion, they retain clear patterns. But now they were bending, very slightly, very precisely. It was a spectral curvature, as if the frequency space the lines were travelling through had warped. Not enough to displace the central wavelengths, but enough to alter their vector across the diffraction pattern. It looked like the spectrum had passed through a lens, except there was no lens. This type of deformation has only been recorded once before, during gravitational lensing events near massive celestial bodies like quasars or black holes. But 3I-ATLAS isn't massive enough to bend light this way, not even close. So what caused it? Initial analysis suggested an interference field, a structured region of space surrounding 3I-ATLAS, where light behaves differently. Not absorbed, not scattered, but redirected. It's a concept known in theoretical physics as a phase space alteration, where the properties of light propagation are altered, without the involvement of traditional mass or medium. Essentially, the path of the photon is bent, not by gravity but by structured energy. This would be unprecedented for any comet. Even for an artificial probe it would be revolutionary, but the ISO team checked, double-checked, and ruled out all known causes. No atmospheric distortion, no mechanical misalignment, no calibration error, no detector heat warping. The signal remained stable, reproducible, and clearly offset. At exactly 1712 UTC, the bending ceased. Emission lines returned to normal. This temporal boundary became critical in triangulating what might have caused the effect. Within the same 10-minute interval, telescopes in South Africa and Japan also registered small, localized changes in polarization across the same band of emissions. It was as if the entire sky, briefly, shifted in how it carried light from a specific direction, and the only object located at the convergence of those vectors? 3I-ATLAS. What's more intriguing is which lines bent. The distortion wasn't across the full spectrum, it was targeted. It only affected certain molecules, notably nickel, carbon monoxide, and hydrogen sulfide. All three are commonly found in comets, but also in communication-grade plasma shielding experiments on Earth. In laboratories testing magneto-optical materials, these molecules show line curvature under controlled interference from EM fields, which raises a simple, staggering question. Was 3I-ATLAS manipulating its spectral fingerprint? Why would it do that? One answer: concealment. By altering the linearity of emission lines, any Earth-based spectrogram would return faulty chemical readings, masking internal structure, surface composition, or artificial signatures. Another answer: targeting. Some researchers believe this kind of phase bending could be a way of pinpointing resonance, actively scanning for specific molecular responses in Earth's atmosphere, oceans, or even biology. Because certain proteins and neural chemicals on Earth also share overlapping absorption bands, if something wanted to know not just where we are but how we're built, this would be the method. But perhaps the most chilling hypothesis is the simplest. It's watching how we observe. By shifting its own spectral behaviour, 3I-ATLAS may be triggering experiments, seeing how our sensors respond, how fast we recalibrate, how much we understand. And when the scan ends, the lines straighten, the light returns to normal, and we're left staring at a spectrum that was never fully ours to read. At 1746 UTC, multiple geostationary satellites positioned above the central Pacific Ocean began reporting simultaneous data losses, specifically in telemetry readings, atmospheric profiles, and high-frequency radar reflection. The satellites themselves weren't damaged, their communication links remained intact, but their instruments, dozens of them, across different agencies, registered the same, impossible reading. Nothing. In a sector spanning over 300 kilometers in diameter, atmospheric density maps returned flatline values. No clouds, no pressure gradients, no water vapor, no Doppler wind signatures. The entire volume behaved as though it had been digitally erased, a black hole not in space but in data. This was quickly dubbed the null zone. It formed roughly 1,000 kilometers southwest of the Hawaiian Islands, in an otherwise quiet stretch of ocean known for relatively stable weather and minimal electromagnetic interference. The event lasted for 11 minutes. What was most disturbing wasn't the silence, but the symmetry. From satellite top-down images, the null zone appeared as a perfect circle, sharply defined at the edges. Infrared scans showed a total absence of radiative heat flux, no thermal signature at all. It was not cold, it was not hot, it was invisible. Ocean buoys located within the perimeter continued broadcasting, but their readings also froze. Barometric sensors plateaued. Gyroscopic wave sensors detected no motion, despite nearby regions experiencing normal ocean turbulence. Sea surface temperature dropped by 4 degrees Celsius in under 90 seconds, then flatlined. Even the Earth-observing satellite Suomi NPP, which specializes in thermal anomaly detection, flagged the zone as non-resolving, a term typically used when the instrument fails to detect Earth itself beneath its scan path. To the satellite, it was as if the Earth simply wasn't there. Radar from low Earth orbit platforms couldn't penetrate the region either. VLF radar waves reflected oddly. high-frequency LIDAR returned erratic scatter. The region became a kind of observational vacuum, not physically gone but optically absent. At sea level there were no ships, no aircraft, no eyewitnesses, only data gaps. But then came the final confirmation: NASA's GRACE SFO satellites, which measure Earth's gravitational field with high precision, recorded a momentary flattening of the local gravity map in the null zone's exact coordinates. This shouldn't be possible. Gravitational variations are typically tied to mass distribution, mountains, ocean trenches, tectonic boundaries. But this change wasn't due to new mass. Rather, it appeared to be a neutralization of existing mass in terms of how gravity interacted with it. In simpler terms, the zone still had mass but temporarily stopped interacting gravitationally. The effect vanished after 11 minutes. Every sensor resumed normal operation. Sea temperatures rose. Atmospheric patterns reformed. Gravity returned. The satellites recalibrated without issue, but the data remained, and it pointed to only one direction. At the moment of nullification, 3I-ATLAS was positioned at the exact azimuthal opposition of the null zone, meaning it was on the direct opposite side of Earth from the region. A theoretical energy vector from ATLAS would have passed straight through the planet and emerged in the Pacific. This rules out natural causes. No known Earth-based phenomenon could synchronize this perfectly across satellites, sea-level buoys, radar, and gravimetry. So what was it? Some have proposed that ATLAS initiated a form of remote field testing, projecting a low-energy envelope to interact with Earth's geophysical layers, testing how deeply it could affect the planet's interactive structure without leaving a scar. Others suggest a calibration window, a way for the object to temporarily isolate a segment of the Earth's system to observe how it reboots when returned to normal function. But the simplest theory may be the most unsettling. The null zone wasn't for us. It was for them. A check-in point, a silence field, a location where something could be sent or received without leaving a footprint. Because in that moment, for 11 minutes over the Pacific, Earth didn't just lose data, it lost itself. At 1824 UTC, Earth's network of low-frequency radio observatories began logging a series of unexpected pulses, specifically within the decametric wavelength band, between 10 and 30 MHz. This range is typically dominated by natural emissions from Jupiter's magnetosphere, solar flares, or Earth's own ionospheric activity. But this time, the source wasn't solar, and it wasn't Jovian. The origin was deep space, aligned with the current position of 3I-ATLAS, then just beyond the orbit of the Moon, its tail stretching millions of kilometers across interplanetary space. The first detection came from the Nancy Decameter Array in France. 4 clean pulses, spaced precisely 7 seconds apart with identical frequency profiles. Sharp rise, quick decay, followed by structured interference. Within seconds, the same pattern was confirmed by the US Naval Research Laboratory's low-frequency monitor, and again by the Ukrainian UTR-2 array, which described the signals as exhibiting artificial coherence. Natural decametric bursts, like those from Jupiter, are typically chaotic, wide-band, and smeared by ionospheric refraction. But these pulses were laser-straight in frequency profile, showing minimal dispersion despite crossing vast interplanetary distances. The waveform itself contained nested harmonic oscillations, tiny repeating patterns encoded within the larger envelope, like a signal hidden inside a signal. And perhaps most unsettling, the waveform matched nothing currently listed in the International Telecommunication Union's global database of artificial sources. It wasn't a misidentified satellite. It wasn't a backscatter from solar storms. It was new. Within 20 minutes of the first detection, the pulses ceased, but not before something else was logged. A fifth observatory, Japan's Itat Low-Band Research Station, reported a minor delay in atmospheric entry time of their VLF calibration probe, launched routinely every 2 days. The probe's descent was slowed, not by wind, but by electromagnetic interference in the ionosphere at precisely the same altitude where decametric reflections were recorded. This suggests the pulses didn't just pass by Earth. They interacted with our upper atmosphere. Further analysis revealed that the pulses appeared to refract downward rather than scatter, something that shouldn't be possible unless the pulse was tuned to exploit the changing refractive index of Earth's ionosphere. In essence, the signal curved down into Earth's atmospheric shell. This is exactly the technique used in deep radar tomography, where ground-penetrating waves are shaped to hug the contours of a target region. But here, the target was not rock or mineral, it was Earth's electromagnetic envelope, its conductive skin. Why would 3I-ATLAS do this? Some suggest mapping, others suggest testing atmospheric elasticity, seeing how Earth absorbs, redirects or dampens specific frequencies. But a subset of researchers propose something more sophisticated: carrier testing. In modern telecommunications, decometric wavelengths are almost never used for data. They're too slow, too noisy, but they penetrate deeply, even through oceans and soil. They're the wavelengths of emergency broadcast systems, of submarine communication, of planetary baseline signals. In other words, if something wanted to test how deeply it could reach Earth, without alerting orbital defences or radio networks, it would use this band. And if the pulses were a question, there was something strange about the answer. Approximately 1 minute after the fourth pulse, a backscatter was detected, not from space, but from the South Atlantic anomaly, Earth's weakest magnetic zone. A ripple of ionospheric tension, reversing direction and echoing the final pulse upward. Earth replied, not by intention, not by technology, but by physics, a passive and natural reaction. And 3I-ATLAS recorded it. It was watching for it. Because if you send 4 pulses and Earth echoes the 5th, then you've mapped something no probe ever has. Not just the shape of a planet, but the rhythm of its skin. At 1912 UTC on November 24th, 2025, an atmospheric anomaly was photographed from a commercial flight travelling westbound from Jakarta to Nairobi, cruising at an altitude of nearly 12 kilometres. A passenger captured what appeared to be glowing thread-like structures in the upper atmosphere, delicate bluish-white wisps reflecting sunlight far after the local sunset. The flight crew, initially dismissing the observation as cirrus clouds, was quickly corrected when onboard equipment detected unusually cold conditions near the mesopause, far above the cruising altitude. Upon landing, atmospheric researchers reviewed the footage and made a rare but unmistakable identification: noctilucent clouds, but in the tropics. These clouds are known to form near the polar mesosphere, typically at latitudes above 50 degrees, where summer temperatures in the upper atmosphere drop below minus 130 degrees Celsius, allowing tiny ice crystals to form. They float between 76 and 85 kilometres above Earth's surface, catching sunlight from beyond the horizon and glowing with an eerie luminescence. But tropical regions aren't supposed to see them. Not in November, not at all. Within the next 3 hours, additional sightings came in from southern India, coastal Kenya, and remote Pacific islands, all describing similar luminous veils gliding across the night sky. Amateur astronomers confirmed the elevation of the clouds using triangulation and image stacking. They weren't hallucinations, they were real, and they were moving. The tropical mesosphere, typically too warm and turbulent for noctilucent cloud formation, had suddenly cooled by nearly 25 degrees Celsius, according to balloon and satellite data. The cooling was fast, localized, and completely unexplained by standard meteorological models. This wasn't just a climate fluctuation, it was an injection event. Atmospheric probes detected elevated levels of micrometeoric dust and exotic ice nuclei, unlike anything previously recorded at these latitudes. The particles were highly uniform in size, measuring just under 100 nanometers, and chemically coated with compounds like magnesium silicate and trace nickel oxide. Where had they come from? The timeline coincided exactly with the decometric radio pulses emitted from the direction of 3I-ATLAS just an hour earlier. While seemingly unrelated, the pulses had passed directly over the equatorial atmosphere before curving downward. One hypothesis suggests they triggered a coherent resonance, allowing particles, perhaps embedded in the outer tail of 3I-ATLAS, to settle into the atmosphere with unusual stability. And when those particles met the right temperature conditions, noctilucent formation began. But this time it wasn't just beautiful, it was structured. High-resolution photography from ground-based telescopes revealed something strange. The clouds weren't diffuse or random. They formed layered bands spaced with mathematical regularity, like harmonics in a stringed instrument. Even more bizarre, the bands slowly drifted eastward, at a speed inconsistent with mesospheric winds. It was as if they were being pulled, not pushed. NASA's Atmospheric Chemistry Division began simulations. Initial models failed. No known mechanism could account for the sudden cooling, the exotic nuclei, and the tropically confined cloud formation, unless an external organising force had momentarily altered the thermal structure of the entire upper atmosphere. Was 3I-ATLAS testing atmospheric manipulation? Noctilucent clouds are fragile, delicate, and extremely sensitive to environmental change. They're the perfect indicator species, showing when the mesosphere has been touched, even briefly, by energy systems we don't yet understand. And now they were glowing in places they've never been seen. Glowing in harmony. Glowing with symmetry, not a message, not a warning, just a presence. The sky had been changed, and long after the radio pulses stopped, long after the clouds faded, the atmosphere remained just a little colder, as if something had passed through and left the air itself remembering. At 20:06 UTC, a quiet alert was logged by the automated environmental monitoring system stationed at the Arecibo Observatory site in Puerto Rico. Though the main dish was decommissioned years ago, the facility still hosts a range of sensitive sensors, including long-wave atmospheric thermometers and ionospheric detectors, maintained by both academic and military institutions. The alert wasn't seismic, it wasn't electromagnetic, it was thermal. Within a 5-minute window, air temperatures around the Arecibo site dropped by 3.6 degrees Celsius, a statistically significant change, especially given the time of day, stable weather conditions, and absence of cloud cover. The descent was smooth, non-linear, and uniform across sensors placed at different altitudes, but what made it more unusual was where the cooling occurred. It wasn't ground-level air that changed first. It was the ionospheric boundary, some 90 kilometers above the observatory, that registered the initial shift. Satellite-based limb scans from the timed spacecraft confirmed that the thermosphere directly above Puerto Rico cooled rapidly, forming a transient sink layer just wide enough to cover the old observatory's collapsed dish. No other region on Earth reported a matching profile at that time, not even nearby Caribbean islands. It was a thermal pinprick, like a scalpel slicing down through the layers of the atmosphere, focused on a single point on Earth's surface, Arecibo. Though no longer active, the site remains historically significant. It was once Earth's most powerful planetary radar, capable of beaming megawatts of energy deep into space. It has scanned asteroids, mapped Venus, and famously sent the Arecibo message in 1974, a binary-coded broadcast aimed at the Hercules globular cluster, attempting to contact intelligent life. The coordinates of that message and the legacy of Arecibo's radar footprint are well documented. So the chilling question arises, was this temperature dip targeted? Researchers analysing the event found that the drop correlated precisely, within 1 minute, with a passing wavefront of polarised solar wind, briefly deflected by 3I-ATLAS's tail. But the velocity and density of the solar wind were not extreme enough to explain the localised thermospheric collapse. Instead, attention shifted to the possible use of radio-reflective materials in Earth's upper atmosphere. During the window of temperature fluctuation, the ion composition above Arecibo shifted, showing an increase in oxygen ions and trace ionised barium, the latter often used in scientific plasma tests to track magnetospheric flows. But no such test was scheduled, no known launch had occurred, and yet there it was, chemical proof of external ion introduction, drifting over a site that once shouted humanity's existence into the void. Speculation began to swirl. Had Atlas responded to the Arecibo message? Or worse, was it already aware of where it originated? If an intelligence had been listening since 1974, the Arecibo site would represent more than geography. It would represent a point of first contact, the first human voice to intentionally cross interstellar space. Now, on November 24, 2025, that point had been cooled, scanned, and possibly tagged. No visible beam was seen, no signal was heard. But the atmosphere changed. As quickly as it came, the dip ended. Air temperatures rebounded. The thermosphere's profile returned to normal. Satellite paths showed no anomalies, but the chemical traces remained in the archive, logged, confirmed, and unexplained. Whatever passed through the sky above Arecibo did not stop. It didn't break anything. It simply touched the air and left us wondering, Did something remember our voice? Did something come back to find the place where we first said hello? And if so, why the silence now? At 2048 UTC, operators at the Geostationary Operational Environmental Satellite, GOES-16, Command Center began receiving image artifacts from one of their high-resolution Earth-facing cameras. The footage, meant to monitor cloud formation over the western Atlantic, displayed a subtle but measurable warping effect, as if a segment of Earth's atmosphere had been slightly magnified and twisted, distorting the curvature of cloud lines and oceanic patterns. Initially dismissed as software corruption, the anomaly was quickly confirmed by two other satellites, Sentinel-3A, operated by the European Space Agency, and Japan's Himawari 9. All three observed the same region and registered the same lens-like distortion, a perfect ellipse hovering above the sub-equatorial Atlantic at an altitude consistent with low Earth orbit. But there was no object, no craft, no debris, just a warping of light. It was as if space itself had refracted, subtly bending light from Earth's surface as though it were being viewed through a curved pane of glass. Optical scientists quickly ruled out known gravitational lensing effects. The mass required to bend light at that proximity would have to be on the scale of an asteroid, but no such mass was present. There were no changes in orbital debris, no sudden flux in local gravity, and no shadow cast against Earth. What bent the light then? One theory surfaced: non-gravitational lensing. In laboratory settings, plasma fields with highly tuned electromagnetic profiles can cause localized refraction. Known as plasma lensing, this technique has been proposed for long-range communication and beam focusing, but never observed naturally, and certainly not on a planetary scale. Yet the footprint matched plasma lensing signatures exactly. Uniform outer edge, smooth central magnification, reversible curvature with no thermal shadow. Even stranger, the effect lasted for exactly 222 seconds, then vanished. Not gradually, instantly. And just before it disappeared, one final satellite, a CubeSat operated by a student group in Brazil, captured a faint spectral shimmer at the edge of the lensing zone. Spectral analysis showed no material object. But there was something else. The region carried a nickel-rich signature, identical to what had been previously traced in the coma of 3I-ATLAS. The implication was immediate and unsettling. If 3I-ATLAS was capable of generating or emitting structured plasma fields remotely, targeting Earth's orbit with enough precision to create a lens in open space, then it wasn't just observing, it was calibrating. A lens is not a passive phenomenon, it's a tool, and a lens this specific could have only one purpose: to focus. Focus what? Some suggested it was scanning, focusing Earth's electromagnetic reflection back toward the object to refine its sensing resolution. Others speculated about directed energy reception, a kind of resonant mapping of Earth's biosphere and atmospheric contents. But a few researchers, working quietly within defense-funded labs, proposed something darker. In advanced optics, a converging lens doesn't just read data, it can also deliver it. In this view, the lens was one half of a communication system. Earth may have been the passive receiver of an incoming signal, one that bypassed all traditional frequencies, ignored human listening stations, and instead used space itself as the medium. That theory gained weight when, 6 minutes after the lens vanished, an unusual ripple was recorded in the Van Allen radiation belt, a short-lived shift in particle density along a narrow corridor that aligned exactly with the prior lensing zone. Something had passed through, or been sent. Not a spacecraft, not matter, but a beam, an invisible thread woven through space, seen only because it briefly bent the light around it. And when it ended, there was nothing left to see, except 3 images from 3 satellites perfectly overlapping, and a silence that followed. Not from failure, but from completion. Something had looked through Earth's atmosphere that night. And perhaps, just for a moment, it saw something looking back. At 2126 UTC, a cluster of undersea listening devices, known as hydrophones, operated by the Comprehensive Nuclear Test Ban Treaty Organization, CTBTO, began logging low-frequency resonances in the southern Atlantic Ocean. These hydrophones, positioned near the Ascension fracture zone, are designed to detect underwater detonations or seismic events with extreme sensitivity. But this sound wasn't seismic. It wasn't natural. It was a tone, specifically a clean oscillating wave at 2.3 Hz, modulated in repeating 17-second intervals. The signal was beyond the threshold of marine biology, and unlike the transient chirps of whales or the broadband rumbles of tectonic shifts, this resonance had structure, coherence, and it lasted for 3 minutes. The tone was omnidirectional, arriving simultaneously at hydrophones spaced thousands of kilometers apart, yet showing no discernible point of origin. Instead of behaving like a localized acoustic event, it functioned more like an ocean-wide hum, with the same frequency profile emerging from opposite ends of the array. To acoustic scientists, this was immediately familiar and deeply concerning. It mimicked the Earth resonance modes, fundamental vibrations of our planet excited by large quakes. But this event lacked any seismic trigger. It did not emerge from the crust. Instead, it propagated through the water column and rebounded off the deep thermocline, indicating a source that originated neither from the seafloor nor the sky above. The data suggested the ocean itself had been used as a resonant chamber, struck gently by an unknown, possibly external force. One researcher compared it to the effect of tapping a wine glass. Not enough to shatter it, just enough to make it sing, and sing it did. At precisely the same time, remote submersible sensors deployed by the Woods Hole Oceanographic Institution in the Puerto Rico Trench registered a subtle pressure wave, as though the ocean's molecular tension had briefly softened, like fabric bending under a steady hand. Yet there was no rise in temperature, no disruption of salinity, no biological reaction from marine fauna. The fish did not flee. The whales did not react. It was as though the signal had slipped through the biosphere, touching only the structure of the ocean itself. So why is this important? Because the frequency, 2.83 Hz, was not random. That exact value had been observed before, once. It matched a spectral component found within the decametric radio pulses emitted by 3I-ATLAS earlier that same day. A secondary harmonic, barely perceptible, nested within a far broader radio envelope. It now seemed that harmonic had a physical twin, not just in the electromagnetic spectrum but in Earth's fluid layer. The implication was staggering. A signal had crossed mediums, from radio into water, from vacuum into mass, and it had retained its integrity. Further modelling revealed that such resonance could only occur if a precisely shaped pulse had entered the Earth's magnetosphere, passed through the magnetohydrodynamic boundary, and translated, without degradation, into acoustic vibration within the sea, a kind of interdimensional handshake between fields. But the real concern came not from the physics, it came from the timing. Exactly 11 seconds before the resonance began, 3I-ATLAS was observed aligning momentarily with the Earth-Moon barycenter, the gravitational balance point between our planet and its satellite. Some speculated that the timing wasn't coincidental, that perhaps the ocean was chosen not for what it holds, but for what it connects. Water is the only substance that exists on Earth's surface in all three phases: solid, liquid, gas, and it transmits mechanical energy more efficiently than air or soil. To use it as a carrier would be natural for any intelligence capable of interacting with planetary structures, and if that was the goal, to send a pulse not just through Earth, but into it, then this wasn't just a resonance, it was a knock. And now we have to ask, what or who was meant to hear it from below? At 21:55 UTC, scientists at the Sofia Airborne Observatory, then in its final weeks of operational calibration, completed a set of high-resolution infrared spectral scans of 3I-ATLAS's tail structure. The data, streamed in real time to multiple institutions across the US and Europe, revealed something both familiar and unsettling. Amid the volatile dust, frozen gases, and mineral particulates already known to trail behind the object, one specific spectral fingerprint stood out. A concentrated band of emission lines centered around 10.8 microns, associated with ionized nickel. This wasn't the first time nickel had been found in a comet, but what startled researchers was the stability of the signature. Across all prior observations of 3I-ATLAS, ranging from deep sky telescopes to planetary orbiters, this same nickel emission profile had remained not only present, but unchanging. From its first detection months ago through solar perihelion and now into Earth's orbital vicinity, The comet's nickel signature had maintained the same molecular density, particle charge ratio, and distribution arc. That's not supposed to happen. In known comets, elemental emissions like nickel vary wildly over time. Sunlight, solar wind, outgassing, and thermal expansion alter chemical concentrations. Nickel, being dense and metallic, usually clumps near the nucleus and disperses erratically. But 3I-ATLAS was different. Its nickel field wasn't random, it was engineered. The spectral line exhibited properties associated with molecular confinement, as if the particles were regulated by an external force. The field surrounding them was not diffuse, but layered, like sheets of charged dust, behaving in lockstep with one another, rotating, undisturbed by the chaos of interplanetary space. This level of continuity had never been seen in natural cometary behaviour, and then came the comparison. Archived data from the Giotto mission, which flew past Halley's Comet in 1986, contained a single partial trace of ionised nickel during the inbound leg. That signal had quickly degraded within hours, but the 3I-ATLAS nickel band had persisted now for 147 consecutive days. Continuity at this scale suggests artificial stabilisation, perhaps even structural reinforcement, a lattice of nickelized material maintaining its shape, orbit and emission pattern with millimetre precision across millions of kilometres of motion. One theory proposed by researchers at the Max Planck Institute: the nickel is not a residue, but a carrier medium, intentionally seeded into the tail to preserve field symmetry and encode spatial information. In this view, the nickel field acts as a kind of breadcrumb trail, allowing precise recalibration of orbital mechanics, environmental interaction, and rotational state. It would be the equivalent of a mission log, visible not through data packets, but through chemistry. Another theory is more functional, that the nickel tail acts as a cooling sheath, allowing internal components within 3I-ATLAS to dissipate heat in a passive, long-duration form, releasing energy through controlled atomic vibration rather than radiation or ejection. But the most intriguing theory comes from physicists specialising in signature persistence. They noted that the nickel profile's consistency was so precise it bordered on temporal symmetry, meaning if one reversed the observational timeline, the signature would appear unchanged. That's not just spatial continuity, that's causal neutrality, an indication that whatever is controlling this emission exists outside of traditional entropy curves. If true, it implies a feedback system with near-perfect memory of its previous state, a kind of field recall, where the object can reassemble its trail, recalibrate its motion, or even trace its own steps backward if needed. This turns the comet from a passive traveller into something else entirely, not a wanderer, not even a probe, but a loop, a machine built to persist, to remember, and to continue, independent of external chaos. And so the nickel signature tells us something profound, that no matter what Earth's atmosphere does, no matter how much light, heat or pressure it faces, 3I-ATLAS remains unchanged, and perhaps that's the point. Not to adapt to the universe, but to show the universe what consistency looks like, even in the face of time. At 22:18 UTC, a coordinated sweep of Earth's upper atmosphere began, led by a joint research team from the National Centre for Atmospheric Research, NCR, and the University of Kyoto. Their goal was to test long-range radio propagation models following recent anomalies caused by 3I-ATLAS's tail sweep. Using high-altitude balloons, microwave scatter arrays, and satellite reflectometry, the teams expected a standard profile of atmospheric pressure gradients. What they found instead was a shift, not a collapse, not a spike, but a precise layered compression, targeted within the narrow vertical corridors known as atmospheric waveguides. Waveguides are invisible channels in the atmosphere, regions of density and temperature contrast that trap certain radio frequencies, allowing them to travel thousands of kilometres without significant loss. They're responsible for transcontinental signal bounces, submarine communication systems, and even parts of the global lightning detection network. But on the night of November 24th, one of these channels had subtly changed. A pressure ridge, exactly 6 kilometres wide, had formed in the D layer of the ionosphere, sitting between 70 and 90 kilometres above sea level. This ridge wasn't global. It tracked from the western coast of Africa, arced over the South Atlantic and terminated near the Chilean coast, following a nearly perfect geodesic curve. The ridge's properties were unusual: uniform amplitude across its entire arc, sharp refractive edge without thermal bloom, and most mysteriously, a modulating pulse envelope at exactly 9.42 Hz, a frequency only loosely used in ELF submarine communications and never seen in natural atmospheric conditions. The pulse wasn't loud, it wasn't even energetic, but it was persistent, oscillating at fixed intervals with microbar variations in local pressure. It pulsed for 18 minutes before vanishing completely. What was most compelling was how it interacted with existing radio traffic. Long-wave transmissions passing through the corridor were slightly amplified, just enough to be measured. Signals sent from Cape Verde to Buenos Aires experienced a 0.6 decibel gain. When repeated using a different angle outside the corridor, the gain vanished. This was no fluke of weather. This was waveform augmentation, as if the atmosphere itself had been tuned into a lens for energy propagation. One senior atmospheric physicist compared it to an organ pipe being briefly reshaped while sound was flowing through it. Another likened it to a flute being played by fingers that weren't ours. Why would a pressure ridge enhance communication? Theoretical models suggest this may have been a deliberate use of low-pressure stratification to create a non-scattering corridor, a segment of sky temporarily shielded from chaotic ionospheric activity, built to facilitate either incoming or outgoing communication. In practical terms, Earth had grown a temporary nerve fibre. Further intrigue emerged when the pressure pulse was cross-referenced with surface magnetometer data from Chile, Brazil and Namibia. At each ground station, tiny fluctuations in the local geomagnetic inclination occurred precisely every 942 seconds, matching the atmospheric pulse overhead. A pattern had formed: air pressure, magnetic tilt, signal boost. 3 modalities, 1 effect. But the mystery deepened when satellite LiDAR over the South Atlantic captured a faint vertical column of aerosol activity rising from the ocean surface directly beneath the midpoint of the waveguide arc. The column was colourless, fast-moving, and left no thermal trail, but it rose to 70 kilometres in under 4 minutes, penetrating the ridge and then disappearing into the upper thermosphere. Had something passed through the waveguide? If so, was the structure built for transmission or entry? Either way, the implications are profound. The atmosphere isn't just reacting, it's being reconfigured, temporarily reshaped, one corridor at a time, in places we can barely measure, let alone control. What we witnessed wasn't chaos, it was design. Atmospheric architecture on a planetary scale. The sky didn't fall, it folded, and for 18 minutes on November 24th, Earth's atmosphere became a channel, not for what we said, but for what we heard. At 23 or UTC, ground control teams at NASA's Goddard Space Flight Center confirmed a system-wide data freeze in one of the low-priority telemetry streams from the James Webb Space Telescope. The stream, primarily a heartbeat feed tracking background radiation and distant stellar noise, had gone silent for exactly 7 minutes and 41 seconds. This wouldn't be cause for alarm under normal conditions. Instruments drift, data buffers fill, autocorrections initiate. But this time, it wasn't just Webb. In that same time window, 3 other satellites positioned near the Earth-Sun Lagrange Point 2, commonly known as L2, also failed to log any passive signal variation. These included ESA's Euclid Telescope, the Gaia Observatory, and the joint NOAA-ESA Solar Sentinel prototype platform. Each of these spacecraft is built with different instruments, separate telemetry systems, and independent clocks. But they all went quiet, together. The L2 point, located approximately 1.5 million kilometres behind Earth from the Sun's perspective, is one of the most stable observational platforms in our solar system. Instruments here face outward into the deep, cold void, constantly surveying the universe's faintest echoes. Noise is expected, static is expected, even cosmic ray strikes are routine, but not silence, and certainly not synchronized silence. When engineers investigated the logs, a subtle anomaly emerged. In all 4 spacecraft, just before the signal collapse, a sudden drop in background microwave radiation was recorded, less than 1 degree Kelvin in deviation, but statistically significant. It was as if the entire field of view around L2 had been momentarily dimmed. Not from an obstruction, not from equipment failure, but from the absence of expected chaos. In the silence there was order. This pattern mirrors what astrophysicists call null lensing, a condition where an unknown field or object passes between the observer and background radiation, but instead of bending or scattering the incoming energy, it absorbs it completely, leaving behind a void with no diffraction halo, no spectral echo, and no geometric distortion. It's the closest thing we have to observational erasure. The incident lasted for 461 seconds, and when it ended, the data returned. Perfectly, with no loss, with no transmission lag, as if nothing had happened. But something had. The synchronization across unrelated instruments, the alignment in phase drop signatures, and the precise duration all point to an external field event, one whose source is yet unidentified. Some suggest this was a gravitational lensing inversion caused by a mass distribution beyond our detection threshold. But no shifts were seen in nearby stars. Others speculate that a dark energy filament might have momentarily swept across L2's vantage point, though no known model supports such a rapid, coordinated null event. Then a new theory arose, quietly, from a small working group in Spain. What if the silence wasn't accidental? What if it was intentional? In this hypothesis, the null signal was a packet, deliberately structured to suppress baseline sensor noise, not by blocking it, but by phase matching it, essentially cancelling the radiation through destructive interference. In other words, not a signal sent, but a signal subtracted. That would require a level of precision beyond anything humanity has achieved. It would mean that somewhere out there, someone, or something, knew the exact frequencies, the exact geometries, and the exact limits of our instruments, and chose to speak to us in silence. No data, no light, no energy, just the sudden deafening absence of all of it, centered on the one point in space where our most powerful eyes are watching. The silence at L2 wasn't empty, it was full of intent, and if you listen closely to that silence, what you hear might not be nothing. It might be the first word of something we weren't meant to interrupt. At 23:31 UTC, a quiet message circulated through a small internal network shared by researchers at the Jet Propulsion Laboratory, Caltech, and the Paris Observatory. The subject line was terse: Model Deviation Breach, 3I-ATLAS. Inside the message was a data packet showing the latest orbital telemetry from 3I-ATLAS. The numbers didn't match, not just in magnitude, but in logic. For months, Earth-based models had predicted a modest trajectory correction as 3I-ATLAS approached its perihelion and later its Earth-adjacent pass. Small changes in velocity were expected, driven by solar radiation pressure, gravity from major planets, and natural outgassing effects typical for interstellar objects. But what actually occurred was something else entirely. Instead of deviating within the accepted tolerance window of plus or minus 0.05 AU, 3I-ATLAS began a non-linear deviation that didn't fit any of the known orbital forcing functions. The shift was curved, not in a Newtonian arc, but in a piecewise vector profile, suggesting multiple micro-adjustments, each occurring at irregular but precise intervals. Earth-based comet models rely on an ensemble of assumptions: that the object is passive, that it responds to gravity and sunlight, that outgassing follows heat exposure, and that motion, once altered, continues predictably. 3SM. Atlas ignored all of these. Its motion was reactive, not to light, not to heat, but seemingly to observation itself. One researcher noted that each time a ground-based observatory captured a high-fidelity spectrum of the object, its trajectory altered slightly in the following 12 to 24 hours. This was observed not once, but 16 times, across different nations, latitudes, and instruments. It was as if 3I-ATLAS knew it was being watched. More conservative scientists pushed back, calling it observational bias or atmospheric error margins. But when compared against space-based assets, including ESA's Gaia, NASA's NEOWISE, and Japan's Hisaki probe, the deviations remained consistent. No matter the method of observation, 3I-ATLAS refused to obey. The standard comet model, one built on gravity, thermodynamics, sublimation, and momentum, could no longer simulate the object's behaviour beyond a 72-hour window. In computational physics, this is known as model collapse. Like a weather forecast that becomes less accurate the closer you get to the storm's centre, the models around 3I-ATLAS began collapsing toward the moment, as if they were being overwritten by a different set of rules, one we didn't write. The last straw came when a new trajectory algorithm designed at MIT using machine learning and trained on historical comet paths failed to converge. The AI halted execution after 3 iterations, issuing a rare stop condition. Insufficient causal anchors. In plain terms, there were no rules left to follow. The implications were staggering. If a single interstellar object can invalidate the foundations of comet physics across gravitational, thermal, and chemical domains, then perhaps the word comet no longer applies. Perhaps 3I-ATLAS is not a comet in motion, but a system in action, something built to interact, to resist modelling, to evolve with attention. A machine not built to be predicted, but to observe the failure of prediction. Some theorists have quietly begun calling this the Heisenberg comet, a nod to the principle that the act of observation alters the observed. But this goes further. This is not quantum indeterminacy. This is intentional opacity. And so, Earth-based comet models have collapsed, not because we lack intelligence, not because our physics failed, but because our tools, our assumptions, were made for nature. And 3I-ATLAS is beginning to feel like something else, a presence that doesn't want to be charted, that can't be captured by formulas, and that moves not just through space, but through the boundaries of what we understand. At 012 UTC, researchers at the University of Geneva's chronobiology laboratory began analysing data from low-frequency magnetic resonance detectors stationed across Europe and Asia. These detectors had recently been retasked to monitor unexplained ELF, extremely low frequency, pulses traced back to the presence of 3I-ATLAS in Earth's orbital environment. What they found was not just peculiar, it was deeply personal. The magnetic pulses were faint but consistent, occurring at a rate of 1 cycle every 86 and 400 seconds, precisely once per Earth day. At first glance, it seemed like coincidence. But deeper pattern recognition revealed a much stranger resonance. The pulses were not tied to Earth's rotation alone. They were slightly phase-shifted, trailing just behind solar noon by 97 seconds, every single day. That offset is critical, because it matches the natural drift of the human circadian rhythm, our internal 24-hour biological clock that, in the absence of light cues, tends to run slightly longer than a solar day. In countless studies, isolated humans, whether underground or in controlled laboratory conditions, default to a cycle of approximately 24 hours and 9 minutes, and now 3I-ATLAS was pulsing at that exact biological offset. The question wasn't just why, but how. These pulses weren't optical, they weren't chemical, they were electromagnetic, so low in frequency that they couldn't be felt, heard, or consciously perceived. Yet they matched the frequency window in which the human suprachiasmatic nucleus, the brain's central timekeeper, responds to both melatonin production and cellular repair cycles. Was this a coincidence of natural harmonics? Perhaps. After all, Earth's Schumann resonances, the planet's own background electromagnetic hum, also operate in ELF ranges. But the pulses from 3I-ATLAS were not globally distributed. They tracked along major population centres. They grew stronger at night, and they restarted every 24 hours, not from a geophysical position, but from human time zones. The pulses didn't follow longitude, they followed the sleep cycle of civilization. That's when a team in South Korea made a chilling observation. When mapped against mobile phone usage, power grid drawdowns, and traffic data, the pulses always peaked when human neurological activity was at its lowest, between 2:30 and 3 a.m. local time. In other words, 3I-ATLAS was syncing with our unconscious state. Some theorized that this was nothing more than electromagnetic mimicry, an object reacting to Earth's fields and by accident resonating with human cycles. But others weren't so sure. The delay offset, the localized nature, and the biological targeting suggested something else. Deliberate resonance. And if it's deliberate, it's not just interacting with Earth's magnetosphere, it's studying us. Further analysis from a sleep research lab in Copenhagen found that on nights with higher pulse coherence from 3I-ATLAS, test subjects entered REM sleep faster, reported more vivid dreams, and experienced a higher degree of neurological synchronization as measured by EEG patterns. Something was reaching into our biology, not to disrupt but to observe, not with light or matter, but with timing. To observe the sleep of a species is to observe it at its most defenseless, but also its most internally structured. Sleep is when memory consolidates, when cells regenerate, when identity refreshes. In the language of systems theory, sleep is when the signal of self becomes most clear. So what does it mean that an object from outside our solar system is aligning with that signal? It means 3I-ATLAS is not looking at what we build or how we speak or even how we move. It is listening to how we dream. The pulses aren't loud, they aren't even invasive, but they are specific. And if that specificity is by design, then we're not just under surveillance. We're being tuned, not disrupted, but calibrated, as if something is waiting for us to wake up. At 01008 UTC, a document quietly circulated within a closed ESA channel titled Eyes on 410A. It wasn't broadcast to public feeds. It wasn't leaked to press. It didn't trigger notifications. Just a silent update, one that reached key personnel at ground stations in Cebreros, Malag, and the European Space Operations Centre, ESOC, in Darmstadt. The document was marked Restricted, Internal Use Only. The subject line read, Anomalous signal drift correlated with 3I-ATLAS object. Do not broadcast. The message was short, just 5 paragraphs. But in those few words it confirmed what many had already suspected. ESA had observed something, and it was holding it back. According to the memo, a composite signal had been detected originating from the general vicinity of 3I-ATLAS, composed of 4 distinct frequency layers, each modulated independently, and carrying non-repeating phase shifts. In technical terms, this pattern didn't match any known natural emission, from comets, pulsars, solar wind interaction, or galactic background noise. It also didn't match anything we had launched. More concerning, the memo stated that the signal drifted slowly, as if adjusting, not to gravitational forces, but to Earth's own electromagnetic profile. This wasn't a one-time ping, it was tracking us. One specific paragraph stood out, due to the unique profile of this transmission, including its sustained coherence over 47 minutes and its synchronized interruption of deep field signal intake across 3 ESA telescopes. All further public discussion of this anomaly is hereby suspended pending internal review. In other words, they shut it down, not because they didn't know what it was, but because they might. What followed internally was even more revealing. Several members of the ESA's Technical Advisory Board, known for their background in theoretical signal mechanics, were temporarily reassigned to non-disclosure departments. A senior astronomer at the La Silla Observatory in Chile had his observational logs from November 24th flagged and restricted, and a compiled waveform graph labelled AT486X, which had briefly appeared on the public FTP server used for interagency sharing, was removed within 23 minutes. No explanation was offered. It wasn't a denial, it was a deletion, and deletion, when done this quietly, often speaks louder than exposure. When independent researchers attempted to request the missing data using ESA's official data query platform, their requests were met with an automated message. Resource temporarily. Unavailable. Please check back after review window closes. But no such review window was defined, and weeks later, the message remained unchanged. The silence didn't go unnoticed. Across the scientific community, encrypted conversations began to circulate. People quietly comparing notes, screenshots, cached data, even second-hand accounts of late-night lab calls. One physicist in Spain allegedly saw the memo moments before access was revoked. He described it as the kind of message you send not because you're afraid people won't understand, but because you're afraid they will. Why would ESA lock this away? The answer may lie in how the signal behaved. The memo hinted that the 4-layer signal didn't just pulse, it reacted. When telescope gain was increased, it shifted amplitude. When the system switched polarization, it flipped phase. It was responding to input in real time, suggesting not just emission, but communication, or worse, interaction. ESA didn't say this explicitly, but their silence implied something unnerving, that the object we call 3I-ATLAS may not just be moving, it may be listening, and if it's listening, then someone, somewhere, decided we weren't ready for what comes next. So they issued a memo. They didn't lie, they didn't explain, they just stopped talking, and that silence may be the loudest signal we've received yet. The question isn't whether 3I-ATLAS is real, it's what reality it's forcing us to confront. Over the past 24 hours, we've seen synchronized pulses, atmospheric reconfigurations, unexplained silences in deep space observatories, and electromagnetic signatures that don't fit any known template of natural behavior. Data has vanished, agencies have gone quiet, models have collapsed. But amid all of that, something stranger has taken hold. We are no longer looking at 3I-ATLAS, it's looking at us. That changes everything. Because for the first time in our observational history, we may be dealing with an object that is not just moving through space, but acting inside of systems. Our systems. Atmospheric, electromagnetic, biological and psychological. It's not broadcasting power, or sending a universal beacon. It's doing something far more intimate. It's calibrating. The pulses match our sleep cycles. The signal profiles match our sensor tolerances. The drift of radiation mirrors our magnetic envelope. This isn't brute force, it's subtlety. This isn't contact, it's context. And the context suggests something that most of our scientific paradigms are not built to handle: an adaptive presence. Think of that. Not a rogue comet, not a failed star fragment, not a silent relic, but something designed to integrate into gravity, into atmosphere, into timing. We've been told to expect first contact in the form of a message, a ship, or a sudden appearance on every screen. But what if it's slower? What if it starts with shadows on sensors? With silence in the spectrum? With systems behaving just slightly out of character? Not enough to alarm, just enough to whisper, "I'm here." Because if 3I-ATLAS is what we now suspect, an artificial or semi-intelligent object adapting to our environment, then we're not at the end of a cosmic mystery, we're at the start of a scientific reckoning. That reckoning has several dimensions. First, our physics. We must now contend with models that fail in the presence of observation. Orbital predictions, chemical expectations, radiation dispersal, all of it breaks down when applied to 3I-ATLAS. It's as though the object introduces a kind of epistemological fog. The more we try to define it, the more it redefines the tools we're using. Second, our data hierarchy. We've always assumed a flow of information from space to Earth, detected, filtered, and processed. But 3I-ATLAS has disrupted that flow. It has inserted itself into the method of observation itself. It responds to detection, aligns with sensor rhythms, and alters coherence depending on where and how it's seen. That's not passive data, that's feedback. Third, our understanding of biological systems. The match between its pulse frequency and human circadian rhythms is no longer something we can ignore. It didn't stumble onto that interval. It held it, repeated it, tracked us across time zones. That implies not just awareness, but a kind of neurological fluency. And last, our readiness. Because if this is what contact looks like, quiet, steady, intimate, then we have to let go of the idea that disclosure will come with a bang. It may come with a pattern, a silence, a map we didn't draw, a pressure ridge we didn't shape, a sky that briefly behaves like it knows we're watching. And now we're left with the final implication. What does it mean now? It means we are not alone, not in the mythological sense, not in the hopeful reach of science fiction, but in the precise scientific sense. Something else is here, not crashing through the sky, but folded into the systems we thought were ours, not to conquer, not to save, not even to explain itself, but simply to exist, to adapt, to witness. And now we are witnessing it back. What that mutual gaze becomes, from here, is no longer just a matter of space science. It's a matter of what kind of species we are when the sky quietly asks us to respond. And the only question left is if we will.